Okay, Year 12, let's talk about esters. So our syllabus dot point is investigate the production in a school laboratory of simple esters. So this one is partnered with a practical. Okay, esters are this functional group here. It looks like a carboxylic acid, but it's got instead of a hydrogen here, it's got another carbon chain on it. Okay? So, esters are formed from the reaction between a carboxylic acid and an alcohol. And you get a byproduct, which is a product that we're not after, we get water as well. Okay? So, if we do a reaction and we get water as a product, we often call this a condensation reaction because water's left over. Okay? So, in general, we've got our R group here on our alcohol and another R group on our carboxylic acid. They come together and we need some help here. We'll get to that in a second. To form this ester that has two R groups, they could be the same, they could be different, and water left over. So here's a nice simple example. I've got methanol for my alcohol, so one carbon there, and I have methanoic acid here, one carbon here. We put them under certain conditions with sulfuric acid as a catalyst and heat, and we get this molecule here that has this ester group and a methyl group on that one. So we call it, and we'll talk more about the naming, methyl methanoate, and water is the byproduct. All right. It looks like I've got a page of extra examples here. I'm trying to find out where. Here we go. This one. Okay. Oh, okay. So that was already on this page. Let's complex it up a bit. Words. Now I've got another example with ethanol, 2-carbon backbone with methanoic acid. What we're getting then is this side group being longer. Now we're getting ethyl methanoate. Okay. So the methanoate hasn't changed because I haven't changed the carboxylic acid. It's the ethyl group that's now changed, which originated from the alcohol. And we've also got the water left over there. Okay. Ethanol again in this third example. But now I've changed the carboxylic acid to butanoic acid. 1, 2, 3, 4. Okay. So now we're forming ethyl butanoate. Okay. So our carboxylic acid, what originated from the carboxylic acid is there, and what originated from the alcohol is there. So it's ethyl. The YL part of the first bit of the name comes from the alcohol, and the butanoate, or the O8, comes from the carboxylic acid. Okay, and water. Okay. So on this slide, I'm just talking about the bonds broken and the bonds formed. Okay, in the chemical reaction, which we're not going to go too in depth in, what ends up happening is the alcohol, the bond that is lost is the OH bond, because that's the weakest bond in the alcohol. It's the most polar. Okay, so the bond between the OH and the alcohol is cut or broken. And in the carboxylic acid, it's the carbon-oxygen bond that's left over. So in green there, the OH and the H come together to form the water. And you get a new bond forming between the O and one of the H's. Okay, so blue is the new bond formed. And for the ester, the new bond formed is between the carbonyl carbon and the oxygen. Okay. So the bonds broken here in the table, I've just represented another way, is the OH bond in the alcohol and the CO bond in the carboxylic acid. Okay, the new bonds that are made are the CO bond in the ester and the OH bond in water. Okay, so here in my example, I've got ethanol with methanoic acid. The OH bond in the ethanol is cut and the CO bond in the methanoic acid is cut. And here in the ethyl methanoate, the new bond is between the carbon and the oxygen and the hydrogen there. Okay, that's pretty hard to remember, but it could come up in an exam question. Okay, uses of esters. Esters commonly have fruity aromas or very, very, they're smelly. Okay, so they're used for perfumes, they're used for flavors. Okay, and they occur in many biological systems. And the smell of fruits and sometimes vegetables, and a lot of things sometimes come down to it having esters in them, okay? And other smelly molecules. We can synthesize or make in a laboratory these molecules, but what ends up happening is there's a difference, and here I'm trying to hint at it with my bananas, okay? So here, I love these diagrams. You can find a few online, but it's an ingredient list for a banana. And you'll notice down here, I've highlighted in green here, we've got a lot of esters. We've got this 3-methylbutyl-1-ethanoate, so it's a bit more complex ester, but it's essentially an ul-OH and an ul-OH there, 2-methylbutyl-ethanoate, and all these, we've got a lot of esters here. We've got about 5 or 6 different esters, okay? So when we come to flavoring, like our fake bananas here, it's very hard and difficult, and it's a lot, well, it takes a lot of work to make not only all these esters in the lab, but to get the ratios and mix correctly so it smells and tastes like a real banana. It'll take a lot of work and it'll be very expensive, but you could do it. You could get it very close. But what ends up happening is, to keep it simple, we choose one of them, and to make it simple, so we only have to make one of them. That's kind of close, but it's not quite right. And that's what we do. So when we flavor banana-flavored lollies, we make 3-methylbutane-ethanoate, this molecule here that I've drawn the structure for, and it smells kind of like bananas, and it tastes kind of like bananas, and we just need to make one of them, and we put it in the flavor for bananas, for the lolly bananas. So that's why lollies and all that tend to kind of be kind of like the fruit, but just a little bit fake. But what it actually is, it's just a little bit simplified. It's just one of the esters that occurs naturally in the fruit that we just put in the flavoring because we only want to make one to keep it simple. All right, let's keep going. Other esters. These are common esters in other fruits, just one of a mix though, okay? So these are commonly the esters that we use for flavoring. If we want a raspberry flavor, we make the 2-methylpropylmethanoate here. And we put that in foods and lollies and stuff like that because it tastes pretty much like raspberry, just slightly weird and different because it's only one and not the mix that's actually in the raspberry. And so here we've got some others, some ones for apples, we've got peach here, we've got one of the orange ones, coconut one, and we've got the pineapple one as well. Okay, so we can make these flavors in the and aromas in the lab. And I love this diagram. I found it online. What it is it's a whole bunch of esters and a pictogram of their flavor. Okay, so here we've got the alcohol that goes into the ester to make the ester, and here we've got the carboxylic acid. So this one here, they're saying smells and tastes like banana. It is 2-methylpropylbutanoate, or it comes from 2-methylpropanol and butanoic acid. When you do a esterification reaction between those, you get a banana flavored ester. Let's choose another one. I like this one. I've tried to make this one, but it doesn't work out that strong. But this one is from carboxylic acid called salicylic acid, and butyl alcohol or butanol, butanol. You react those together in an ester reaction and you get this kind of blackberry smell. Still trying to make that successful, okay? So I love this kind of diagram. It's got a variety of different options there. Okay, I've just added in, here's the same person who made these ingredients list. I love them. There's one for the passion fruit, there's one for the kiwi. Have a look in these green highlights that I've put in there. They're all the esters that are in them, the mix of them. So there's quite an awful lot. Okay, on to naming esters. Esters consist of 2 words with a space in between. Yeah, remember all those times in organic naming and I'd be ranting, don't put a space in, don't put a space in. Esters, they need a space between them. Okay, so they're 2 words. The first word is the alkyl group. that originated from the alcohol. Okay, so it's going to be methyl, ethyl, propyl, something, ul. Okay, and that came from the alcohol. The second word is kind of like the conjugate base of the carboxylic acid. Okay, so it's like methanoate, ethanoate, propanoate, not propionoate, propanoate, butanoate. Okay, so the form is alcohol and then the acid OH. Okay, so here's my example. I've got three there, and that has the ester group on it. So that came from the carboxylic acid. So it's 1, 2, 3. So it must have been propanoic acid. So it's a propanoate. Okay. Here on the alcohol originated bit, I've just got one carbon. So it must have came from methanol. So it's a methyl space. Oh, this example doesn't give a space. Methyl propanoate. Okay. So the first word comes from the alcohol. The second from the carboxylic acid. Here's some examples from the textbook. I like how they color-coded them. Ethyl, because that bit came from the alcohol, and then the propanoate. 3 carbons there, okay? So here in blue, it came from the carboxylic acid, and here came from the alcohol. So it's methanoate, and it's 3, so it's propyl methanoate, okay? So let's do a couple of examples. We've got to name these ones. Oh, a few. We can do it, though. All right, maybe I'll change colors because there's red in there. Okay, so find the CO bond that's not with the carbonyl. There, okay. Oh, actually, that's not the new bond. This is the new bond, okay. So this side came from the alcohol, so it must have been ethanol. And this side came from the carboxylic acid, so it must have been ethanoic acid. So it's ethyl ethanoate. Okay. Here, this one here is, oh, hang on. No, I've got that wrong again. This bond is the new bond, okay? The carbonyl came from the carboxylic acid, so it's a methanoic acid, so it's a methanoate. And 1, 2, 3 with the alcohol, so it's a propyl so propyl methanoate. I left the big gap there, leave it smaller. Okay, here, new bond. Okay, this side is the alcohol, so it's a ethyl, and this side, benzene with a carboxylic acid, so it's a benzenoic acid, or it's a benzoate. Can't write. There we go, benzoate. Okay, new bond here in this one, alcohol. So it's a propyl, meth propyl. And this side, 1, 2, 3, 4, 5, it came from pentanoic acid. So it's a pentanoate. Okay, last one. New bond is here. So the alcohol had 1 carbon, so it's a methyl. 1, 2, 3, 4, 5, 6 carbons for the carboxylic acid, so that's a hexanoic acid, so it's a hexanoate. So that one's a methyl hexanoate. All right. Draw a structural equation for the reaction between methanol and butanoic acid. Name the products. Okay, methanol. 1 carbon. There's our alcohol. Fill in the hydrogens. So there's methanol. And butanoic acid. But 4. 1, 2, 3, 4. It's a carboxylic acid, so put the carbonyl and then the OH. Fill in my hydrogens here. Okay, the reaction is because we've got an alcohol and a carboxylic acid. Oh, I'm going to do a bit of dodgy here because I'm running out of room. It's a what's the word that I'm looking for? Equilibrium reaction. We need sulfuric acid, concentrated, and heat. Okay, and what we produce is, well, let's talk about, I'm going to mark in a different color, what bonds are broken. Okay, do we remember that bond there and that bond there? Okay, so I'm going to write water as my product, and let's do the ester product here. Should we go back to blue? Okay, so let's do the O8 bit, carbonyl, and three more carbons. Put your hydrogens around. One more. Okay, and then it would have bonded to the oxygen of the alcohol, and then there was just one carbon there. Okay, name the products. Water. And this one, methanol, so it's now methyl, and butanoic acid, butanoate. So it's methyl butanoate as the product, and water as the other product. All right, draw the structural equation for the production of propyl butanoate. Identify all the bonds that break at the newly formed bonds. Okay, well, let's draw propyl butanoate. Prop, three carbons, and then it came from an alcohol, so it's got the one oxygen. So there's my propyl branch, and then will be my carbonyl that came from the carboxylic acid. What carboxylic acid did we have? Give me a second, just putting in hydrogens. Butanoate, so we need 4 carbons. 1, 2, 3, 4. Okay, put in my hydrogens. So there's my propyl butanoate. Let's just check. 1, 2, 3 for my alcohol, good, and 4 for my carboxylic acid, good. All right, don't forget water is the other product. Okay, working backwards, we've got an equilibrium reaction. Sulfuric acid, heat, and it's conc sulfuric acid that we usually use. Okay, so it must have come from an alcohol. The propyl came from the alcohol, so it's going to be propan-1-ol. And butanoic acid. 1, 2, 3, 4. With my carboxylic acid head there. Fill in the hydrogens. Okay. Identify the bonds that break. Okay. The bonds that break. Can I recall it properly? Okay. The OH bond in the alcohol breaks and the CO bond in the carboxylic acid breaks. Okay. So therefore the new bond goes from the oxygen of the alcohol to the carbonyl. Okay. Oxygen to the carbonyl. So this is a new bond. And it doesn't matter which one you put on the water because it's symmetrical. New bond. So break and break. Okay, draw the structural equation for the production of this. Yep, propyl butanoate. Identify all the bonds that break and the newly formed bonds. I think we've done it. All right, properties of esters. Let's keep going. Okay, we're determining if it was polar. Okay, so we've got carbon-oxygen bonds here, which are polar, and we've got a carbonyl here, which is polar. Okay, they're not equal and they're not opposite. So we must have a net dipole for esters. So esters are polar molecules. But notice, they do not fit the criteria for the really, really strong polar molecule that can do hydrogen bonding, okay? Because we haven't got a hydrogen bonded to an oxygen there. They're all bonded to the carbons, okay? So when two esters come near each other, they interact with dipole-dipole attraction and dispersion forces, but not that really, really strong dipole-dipole attraction, which we call hydrogen bonding, okay? Most esters are insoluble in water because they cannot form hydrogen bonding with water, okay? So you mix water and you mix an ester together, and water sticks together so strongly that it doesn't really want to interact with the ester, okay? All right, so many organic substances will dissolve in esters. So a lot of non-polar stuff will dissolve in esters, so it's a really good solvent, okay, for organic molecules that don't dissolve in water. So esters are often used as solvents in industry. An example is ethyl ethanoate is common as an ester in nail polish remover, okay? So along with your acetone and stuff like that. Okay, here's some formula and properties of common esters. Notice that the molecular mass is going up, and you can see that the boiling point is going up as well. And it's really only to do with dispersion forces, because we're just lengthening those carbon chains. And you can see as the carbon chain lengthens as well, they're becoming less and less, well, that polar part is being kind of drowned out, so the solubility is going down, the solubility in water. Okay, a little bit more detail on actually making these. So the reaction is an equilibrium that's not spontaneous. So most esterification reactions have Gibbs free energy values in the low positives, very low positives. So we've got to kind of like think about Le Chat when we're making this as well, trying to push it towards the product side. So we can, this reaction still happens slightly, but if we want it to happen quicker, like if we're making it, we use a catalyst, and that catalyst is a good one that we're using all the time in organic chemistry: concentrated sulfuric acid and heat to increase the collision rate of those reactant molecules. So as I just said, we use Le Chat's principle to shift the equilibrium to favor the product side and increase our yield, so increase the amount of ester that's being produced. Okay, so some of these conditions, it's a slow reaction, and it has an equilibrium constant below 1, so we need to speed it up. So one thing we talked about is heating it. Now the problem with heating your reaction vessel when you're trying to make an ester is that your carboxylic acid and your alcohol are going to heat up and evaporate away. They're going to turn into a gas. And once they're lost, you can't react them. So, I'm talking about what's on the next page. So I'll just skip ahead and talk about that. So the low boiling points of our reactants and our products, if we start heating them, we're just going to boil them away. What we can do is reflux, okay? What we can do is set up our reactants down here, and as they heat up, they're coming into a condensing tube, like when we do distillation. But here, that condensing tube is vertical. So it goes up as a gas, it's going to condense on the walls and cool down and drip back down into our reaction vessel. So the idea is we want to heat up but not lose any gases, so we're using a condenser directly above so it drips back down. So when you're doing this actually practically, if you're seeing some vapors come out, what you need to do is you're running it too hot and you need to cool it down a bit. So put some more water in there and stuff. Adjust the temperature. You're losing some stuff. Okay. Also, the danger with heating up is that many of these organics are flammable. Okay. So using a Bunsen burner or an open flame is not ideal. It's not too bad, but it's not ideal. If you're doing it in a fume cupboard, it's not too bad. But what is ideal is, look what they've got here. They've got something called a heating mantle. And a heating mantle is just an electric heater that has a circular bit in it that you can drop that round bottom flask into. And it just uses like resistance, so an electrical coil to heat it up. Okay, not an open flame. So that's often come up in safety questions about making esters. Not having an open flame because we've got volatile compounds there, so they're going to be very flammable. So we use a heating mantle instead, so we don't have an open flame. One other thing that we use to increase the yield is we always add in one of the reactants in excess to drive the reaction towards the product side. Okay, so either the alcohol or the carboxylic acid, we dump in a whole heap to try and push it as far as we can. Going back, because I skipped it, Concentrated sulfuric acid is the catalyst that speeds up the reaction, yet is not consumed. Okay, that definition of a catalyst, not consumed. It helps facilitate the reaction, but it's left over at the end. Concentrated sulfuric acid. Once we've done our esterification reaction there, our reflux, we've let it go for about half an hour. Okay, and you can start to safely smell the product in there, but you also smell other stuff like the carboxylic acid. Okay, now what we have once we've done this, because it's an equilibrium reaction, we have got a mixture. Okay, and what we're going to have a mixture of is the products, the remaining the reactants that haven't reacted. We're going to have the products as well. So here I've kind of put it in a table. We've got our ester product. We're going to have some remaining carboxylic acid that didn't react, some remaining alcohol that didn't react because we've got an equilibrium reaction. We're going to have some of our product in this mixture too, some water, which is the product from esterification, and our catalyst also in there. Okay, and some of these are organic and some of these will dissolve in the water that we formed. So what we often see when we've done our reaction is we've got two immiscible layers. We've got our organic layer and our aqueous layer, or our water layer with anything dissolved in it. Okay, and so here I'm trying to show color-wise what will be in each layer. So the water and sulfuric acid will be in that aqueous layer. Okay, the alcohol, the carboxylic acid, I've kind of half blue, half yellow them somewhat. Okay, it depends on that actual alcohol or carboxylic acid, how soluble they are in water. If they're very long carbon chains, they're going to be quite insoluble, and they're going to be in the yellow organic layer. Okay, by the way, I'm just color coding here. They're going to be clear layers when you see them. So the carboxylic acid and the alcohol could be soluble in water, but most of the time they're not, because they're not quite soluble. Okay, so they'll most likely be in the organic layer. Now what we need to do is we need to start a separation process, because we need to get our ester by itself. Okay, so step one, what we do is we add a little bit more water if we need to. We shake it on up and we put it in the good old separating funnel. Okay, so here's our diagram from the textbook of the separating funnel. What we do then is the organic layer will be on top, and the water and anything soluble water will be in the bottom. Our ester will be in the organic layer. So what we're removing is part of the mixture that will dissolve in water. So this is the aqueous stuff, the H2O and anything solubles. And what we'll do is we'll take that out and we'll leave it aside and dispose of that. But we want the organic layer just by itself. Okay, so the aqueous layer will contain water and sulfuric acid, and it could contain short chain alcohols or carboxylic acid that are in excess, but probably not. It depends on the ones that we're using to make the ester. So drain the more dense aqueous layer into a beaker, and we'll put that aside and we'll neutralize it and stuff like that, and we'll keep the remaining organic layer. This will contain our ester and, more than likely, our carboxylic acid and alcohols that haven't reacted. Okay, only a very few short chain ones would be in the water layer. Okay, our next step is, from that organic layer, we want to remove the carboxylic acid that could be in there. And how we do that is we react it with a base. Okay, and we can react it with a base. We choose a specific base. We choose a carbonate in there, so it can keep dumping solid carbonate in there and keep swirling it around, and we keep putting it in until we notice no more bubbles form, and then we know we've gotten rid of all the acid. Okay, so here's our carboxylic acid. So just an example one there. Oh, I've just kind of given our R group on there, and here's our carbonate. We're forming a sodium, a carboxylate ion. Okay, so we're forming an ionic compound and carbon dioxide and water. Okay, so this one, because it's ionic, it will be more soluble in water, and we are forming water. So what we're actually going to end up with is, now we're going to create a new water layer. That's now this product here. Our little bubbles that I've drawn here in white are carbon dioxide, and now our organic compound, well, so our carboxylate will be in the water layer as well because it was ionic, so now it will dissolve, okay? So this organic layer that sits on top, we've gotten rid of the carboxylic acid, so now it contains our ester and any leftover alcohol, okay? How we separate these two? Well, we get out the separating funnel again and we run it back through. We keep that organic layer and we dispose of this new aqueous layer, okay? So this new organic layer, ester and alcohol. So we need a method to separate the alcohol out to just get the ester by itself, okay? And that's a bit harder, okay? So now we've got our organic layer, that's now our ester and excess alcohol. We can use distillation to remove them, okay? Because we've got two organic compounds that have two different boiling points, okay? The alcohol will be capable of hydrogen bonding to itself, and the ester only capable of dipole-dipole attraction. But esters are usually large, so they've got more dispersion forces. So what can end up happening is the ester and the alcohol could have similar boiling points, okay? So it's a bit tricky. You really have to control the temperature in our bottom flask here. For example, if you're making butyl ethanoate, the remaining alcohol is going to be butanol, okay? And it has a boiling point of 118, but the ester has a boiling point of 126. So you've only got a small range to control in there to get separation, okay? So remember, the thing with the lowest boiling point is going to travel up the column and then be condensed and drop down here. Have I got that around the wrong... Yeah, well, I've got that around the wrong way in my notes, haven't I? Oh, that's terrible. So this one is going to be the lower boiling point, and this one's going to be the higher boiling point. How embarrassing. I'll fix that up, okay? So the higher boiling point is going to stay there as a liquid, and the lower boiling point is going to come on through. So it depends on your ester and your alcohol. So your ester will end up in one and your alcohol will end up in the other, but you, of course, before you're going to do this, check your actual ester boiling point and check your alcohol boiling point online to see which one's going to be which, okay? You might be able to smell the difference too, but don't sniff too hard. Okay, we can do a worksheet now, and we've got a prac. And when we do the prac, we can decide, I've put this table in there to decide what esters we could make from what carboxylic acids we have at school and what alcohols we have at school. If you need some more help, there's some questions from the textbook. And next up, soaps and detergents.